in mathematics, a result is not considered to be complete until a proof of the fact has been found. It is not enough to have overwhelming amounts of experimental evidence or to point out the result is consistent with everything else we know. It has to be proved to be accepted. So, our first definition, a statement is an assertion that can be classified as either true or false, but not both. Okay. The more specific you are with mathematical statements, the better. Okay. Within these, we also often will use mathematical quantifiers. There are two mathematical quantifiers, the existential quantifier, which is there exists, and notationally we do a backwards capital E, and the universal quantifier, which is for all, and it is an upside down capital A, notationally. One other thing I want to point out, in mathematics, the words and or have very specific meaning. So and means the same as if you were speaking in an English class, right? Both things must happen. Or, however, has a very different meaning. Okay. It is what's called an inclusive or. So, if I say I can have chocolate or strawberry ice cream, most people assume that means they have to pick one and only one. But in mathematics, we allow you to choose both at the same time. So you could have half chocolate and half strawberry in your bowl. Okay. All right. Negations of statements are the statement that is the exact opposite. So, P and Q will negate to what we refer to as not P and not Q. This is a common way of writing not, okay? P or Q will have a negation, not P. Oh, and look at that, I made a mistake. Okay. P and Q negates to not P or not Q. P or Q negates to not P and not Q. So not only did I negate each statement individually, but I flipped the quantifier. Together, these are referred to as De Morgan's laws. Okay. Why does this make sense? Well, consider a phrase, all cats are black. Now, to prove that the exact opposite is true, I don't have to look at all cats. I just have to find a single cat that is not black. Okay. Similar types of things happen. So, for alls negates to there exists, and there exist negates to for alls. Okay. Another notation that I want to make sure you are aware of, we will often be talking about proofs about something being unique. Okay, so symbolically, the symbol that is the exclamation point means that something is unique. Okay, so if I write there exists a unique cat, I could write it mathematically with these symbols. Okay. So, the most common kind of mathematical statement we will prove is what is called a conditional statement. So, a conditional statement is of the form, if P, then Q. We will often write P implies Q notationally. Okay? If at all possible, every theorem you are trying to prove should be stated in such a form. Okay. So there are various combinations of P and Q being true and false. Okay. So let's look at those combinations and decide if P implies Q, or if P then Q is true or false. So P can be true or false, and within each of those, Q can be true or false. This provides all possible combinations of the truth or falseness of P and Q. By the way, what I'm doing right now is called a truth table. It's a way of organizing the truthness of statements. All right. If P is true and Q is true, then we would say P implies Q is true. Everything is true. Okay. If P is true and Q is false, then I cannot say that P implies Q. Okay. Because if P implies Q is true and P was true, then Q would have to be true. Okay. This does not work. Okay. Now the interesting thing is what happens for my last two, okay, which is when P is false. Okay, consider for me, if you buy me a mansion, I will give you an A in the class. This is a P implies Q type statement. You buying me a mansion is the P statement. Me giving you an A in the class is the Q statement. Okay. Now, I have yet to meet anyone that would like to take me up on this offer. So as far as everyone can figure out, this might actually be a true statement. No one has tested it. Okay. So since no one will buy me a mansion, we are going to give it the benefit of the doubt and assume that if someone actually did, I would follow through with my promise. So regardless of if Q is true or false, if P is false, we are going to assume the statement is always true because we have no evidence to the contrary. Okay. Now, some of the methods of proof rely on logically equivalent ways of writing things. So, the contrapositive of P implies Q is not Q implies not P. So notice, not only did I negate each statement, but I flipped the order of the if-then statement. They are logically equivalent. This means if you prove one, you have proved the other. If one is false, so is the other. Okay. The converse of P implies Q is not P implies not Q. So this time I negated them but did not reverse the order. It is not logically equivalent. Okay. So one of the most common mistakes people make in proofs is they prove the converse and assume that proved the original, and this is not true. Okay. Next, what is the negation of P implies Q? Remember, a negation must have the exact opposite truth values. Okay, so, if you remember our little truth table over here, okay, let's copy it to our new page and try to find something whose truth values are the exact opposite. So whatever my negation is, okay, I want its truth values to be the opposite of here, so I want it to be false, true, false, false. Okay. All right, now I claim that the negation of P implies Q is P and not Q. Okay, so let's try this. I know what P is. Let's compute not Q. It will be the negation of Q, so false, true, false, true. And then P and not Q, well, that requires the P and the not Q to both be true. So true and false, that doesn't work. True and true, that does. False and false, that does not work. False and true, that does not work. Notice, this is exactly the result I was looking for. Okay. All right, we will use some of this notation, some of these equivalences during our proofs-based course. It is just kind of handy to have a way of referring to things and alternate methods of attacking problems.